Hi Year 11, it's Mr. Green here, doing the first lesson on magnets and magnetic fields. We'll start today with some retrieval practice, so if you pause the presentation here for a few minutes while you answer those three questions. Okay, so question 1 asks you to label the characteristics of a wave, and it's labelled them 1, 2, 3 and 4. So they're labelled like this. Number 1 is the wavelength. Number 2 would be the amplitude, the maximum disturbance of the wave. Number 3 is the crest, or you can sometimes call it the peak. And number 4 is the trough, the lowest part of the wave. Question 2, what is the wave equation? Well, that would be speed equals frequency times wavelength. And the last question, what is the electromagnetic spectrum in order of increasing frequency? So that's the wavelength getting smaller as you go along. It's in this order: radio, micro, infrared, visible, ultraviolet, X-rays, and gamma. Okay, so to start for today's lesson, we're going to try and push on with magnets and magnetic fields, and our objective is to know the shape and characteristics of a magnetic field. Our outcomes today to describe the attraction and repulsion between like and unlike poles, to show and state how to draw the shape of a magnetic field around a magnet, and to explain how magnetic fields show the strength and the direction of magnetic forces. So, magnetic materials. Not everything can be a magnetic material, and not every material is attracted to a magnet. Magnetic materials can only attract certain magnets, and these materials are iron, cobalt, and nickel. If any sort of alloy or material contains one of these three types of metal, then it will attract a magnet towards it, and these three materials can be magnetized as well. They can be made into magnets. Magnets have poles, so each end of the magnet has the strongest attraction to these other materials, so we call each end of the magnet the pole. There are two poles. We've got the North Pole and we've got the South Pole, and that'll become important when we talk about attraction and repulsion. Because like poles repel and opposite poles attract, so north would attract south, north would repel north, and south would repel south. So quick check on the board. There are 4 magnets placed in an order there. Pause the video and state 1, 2, 3 and 4 whether the magnets would attract or repel. Okay, let's have a look at the answers for that. So number 1, we have south to south, so that would repel. Number 2, south to north, that would attract. Number 3, north to south, so that would attract. And finally, north to north, which would repel. So the rule is, like poles repel, opposite poles attract. So what makes a material magnetic? Well, magnetic materials contain these little microscopic areas as part of the structure, and these structures are called domains. You can see 2 diagrams on the board there in the presentation. So we've got on the left-hand side the domains before any magnetization has taken place. And we can see the domains are all pointing in random directions. They're not all aligned up, they're all over the place. Whereas in the magnetized one, these microscopic areas are all lined up. They're aligned, they're pointing in the same direction. And this is what gives a magnetic material the magnetic field around it. This is what causes it to attract and repel other magnets. Okay, so for our first progress check, if you pause the video while you attempt these 5 questions and unpause it when you'd like the answers. So if you could pause the video now. Question 1 then. So what materials are attracted to a magnet? It's only those 3. It is only iron, cobalt and nickel. What do we call the ends of a magnet? Well, they're referred to as the North Pole and the South Pole. What's the rule of attraction and repulsion in magnets? Like poles repel and opposite poles attract. What are the microscopic areas in magnetic materials called? They're referred to as domains. And why is a magnet magnetic? It's because the magnetic domains in the material are all aligned in the same direction. Okay, so magnetic fields. Magnets or magnetic materials will attract or repel other materials without even touching them. It's a non-contact force that takes place between them. So in order for them to do that, they have to have an area around them where they will have an effect. We refer to that as the magnetic field. So the magnetic materials will produce a field around them that can affect anything that enters the field. We need to know the shape of the field. we need to know how to use compasses to draw the field, and we need to know how the field is affected when attracting and repelling. We'll go through the first two this lesson, the shape and how to use compasses to draw the field. There's a magnetic field for you, and we can see there are certain aspects of it that you'll need to replicate if you are drawing that magnetic field. So the field lines emerge from the North Pole and they enter back into the magnet at the South Pole. We add arrows to show the direction of the field lines from north to south, so whenever drawing your diagram of this, you need to make sure you're adding those arrows from north to south. We also see that the field lines are much closer together at the poles, and the closer together the field lines are, the stronger the magnetic field. This is why the poles are the strongest part of the magnet. The field lines are much closer together there, the field's having much more of an effect. So whenever you draw in a magnetic field, those two things are very important. You need to show arrows to show the direction of the field lines from north to south, and you need to show how close together the field lines are, and they must be closer together at each pole of the magnet. Then it will have the bigger force and the bigger attraction. To draw one using compasses, so a compass uses a really tiny magnet that lines up with the magnetic field of the Earth, but when we place that near a magnet, the magnet is strong enough to actually attract that compass itself. It overrides the magnetic field of the Earth. So it lines up with the magnetic field of the magnet. Now if we place a number of compasses around a magnet, this can show us the shape of the magnetic field. As you can see on the diagram there, the arrows pointing from north to south, they point away in the direction where they should, and we can see it follows the shape of that field. Now we can use these compasses to plot the field lines. Here's our method. So draw around the magnet and write a small N where the North Pole goes and S where the South Pole is. Draw a dot at the top corner of the magnet. Put your compass next to the top corner of your magnet so the compass needle points away from the dot. Draw a dot on the paper at the other end of the compass needle. Move the compass along so it now points away from the dot you've just drawn. Repeat that process and connect the dots with a pencil. And you do that again for the other side of the magnet. There's two diagrams at the side showing you how to do that process. And again, it will show you the field as we've just seen it in that diagram. Again, pause the video so you can get that method down and you can state exactly what's happening in there. You may be asked for it in the exam. We can also use iron filings to show the shape of magnetic field. So if we shake some tiny iron filings around there, they act as tiny little compasses and they line up with the magnetic field itself. If we shake them around there and we move the paper enough, we can see it will take the shape of that magnetic field. Very similar to what we've already seen. So there's a magnet with the iron filings, and on top of there I've superimposed the magnetic field as we draw it, and we can see it follows that fairly accurately. Okay, another quick progress check. You've got 5 questions there. If you pause the video while you attempt those questions and unpause when you'd like the answers. Okay, so drawing the shape of a magnetic field. Diagram we saw before, we want to make sure we've got that. It's really spacious. You've got north and south stated in there. You've got the field lines emerging from north, going back into south. Arrows are showing that, and they're closer together at the poles. 2 rules for drawing magnetic fields. Field lines will connect from north to south, and we use arrows to show this, and the field lines are closer together at the poles. Question 3, why are they closer together at the poles? Because that's where the magnetic field is the strongest. How could you use compasses to draw a magnetic field? Surround the magnet with compasses, place a dot where the north arrow is pointing to, and then join up those dots. That's a simplified version of it. You've just seen the more complicated version. And you're given 3 materials, a magnet, a piece of iron, and a piece of aluminium. How could you use a magnet to work out which one's which? So if you place the magnet near each one of those materials, if it doesn't attract, that's the aluminium. Remember, magnets only attract iron, cobalt, and nickel. If it only attracts and doesn't repel, then that's iron. Because if it attracts and repels, the only thing that will repel another magnet is another magnet. So that repulsion shows it's a magnet. Okay, to finish off, I'm going to give you an examination question to look through. So pause the video at certain points to read through there. So it shows a magnetic closure box when open and shut. It's a box that stays shut when it's closed due to the force between the 2 small magnets, and they're used for jewellery. Diagram 2 shows those 2 magnets, and the poles are on the longer faces. So we need to draw the field pattern between the 2 facing poles. So have a go at that. Okay, what we should have drawn was arrows going from the North Pole to the South Pole directly across there. Some straight lines that are in the middle of that gap. Question 2. The magnets in the magnetic closure box must not have two north poles facing each other. Explain why. Okay, this is because north poles will repel each other, so the box will not close. 2 marks. You don't get a mark if you don't say the box will not close, only if you say north poles repel. You need both those for the 2 marks. Next one, the student's investigating how the force of attraction between two bar magnets depends on the separation. Uses this following procedure. So she has the Newton meter, a magnet, some sheets of paper in between, and a magnet underneath. She ensures the Newton meter doesn't have a zero error. She holds one of the magnets and puts sheets of paper on top of it. Places the other magnet with the Newton meter magnetically attached close to the first magnet, pulls them apart, and notes the reading on the Newton meter when they separate. She repeats that with different numbers of sheets of paper. Results are in the top right hand corner. Okay, pause it while you have a look at those results and attempt the questions. Okay, question 1. Describe the pattern of her results. So as the paper increases, there's a big decrease in the force needed, and that levels off after around 50 sheets. No matter how many sheets of paper the student puts between the magnets, the force on the Newton meter never reaches zero. Why is that? Because the Newton meter will show the weight of the top magnet, so it is pulling down with the force of gravity. The student is unable to experiment with fewer than 10 sheets of paper without gluing the magnet to the Newton meter. Why would that be? The reason for that is the magnet and the Newton meter separate before the magnets separate, and because of the force between the magnets is greater than the force between the magnet and the hook, it would pull it away from it. 3 improvements to the procedure that would allow the student more accurate results. Any 3 of those that you can see on there, so any 3 of those would be seen as an improvement to the procedure. And finally, the thickness of one sheet of paper is 0.1 millimeters. What's the separation of the magnets when the force required to separate them is 2.1 newtons? What you need to do for this is you need to look back on the table of results. Give you a minute with that. Okay, so we're looking for 2.1 newtons. Read along on your table there. 2.1 newtons is equal to 30 sheets of paper. We know one sheet of paper is 0.1 millimeters, so what we need to work out is what's the thickness of 30 sheets of paper. Simple equation, 30 times 0.1 would give us our answer in millimeters, giving us an answer of 3 millimeters. Okay, hope that was useful. Please review that again to get all the concepts there and try the questions again. I hope you found it useful. See you soon.